So we have to go back actually to something we learned early on in Chem 1, and that's about the idea of isotopes. And anytime you introduce a new topic, there's going to be new words, new terminology that you need to learn. So we're going to review a little terminology that we learned back in Chem 1, and then also to bring up some new terms that we need to learn. Back in Chem 1, we learned about things called isotopes, and we said that they were atoms of the same element, meaning that they had the same atomic number, which is the same number of protons. Okay, remember Z represents atomic number, which also represents the number of protons in the nucleus. But they have different mass numbers. And remember that the mass number is just the sum of protons and neutrons, okay? So for example, there's one isotope of boron called boron 10. Everything that's boron has 5 protons, but in boron 10, you have 5 neutrons. So 5 plus 5 equals 10. And remember the ZXA notation, Z X for the chemical symbol and A for the mass number. So Z is the atomic number, X, if maybe your instructor didn't use that terminology, but this is one way to represent an isotope called ZXA notation, where X is just the chemical symbol from the periodic table, and then A is the mass number, which is the sum of neutrons and protons. So you can have another isotope of boron, boron 11. It still has 5 protons because it's boron, but in this case, in this atom, there are 6 neutrons, and so when you add 6 and 5 together, you get boron 11. All right, so that's what we mean by isotopes. Okay, so another term that maybe you learned in Chem 1, but just to make sure everybody knows what I'm talking about when I use this term, a nucleon is just something that's found in the nucleus. And so it is either a proton or a neutron. Okay, so it's just a more generic word. It includes protons and neutrons. It just means a particle that's found in the nucleus.
Excuse me?
All right, so something I already kind of alluded to, that we're going to focus now on nuclear reactions. And so these are reactions that alter the number of neutrons or protons in the nucleus. So that's the unique thing about nuclear reactions. Nothing really to do with the valence electrons, but we're going to manipulate or change the number of neutrons or protons in the nucleus of the atom. Okay. Another word here, radionuclide. Okay, so it's kind of just a more specific way to talk about an isotope, but it's an unstable isotope. And so these are isotopes that undergo some nuclear reaction, and the type of nuclear reaction that will occur is something called radioactive decay. All right, we'll describe several types of radioactive decay in today's lesson. All right, and here actually is a definition of radioactive decay. So a radioactive decay, what I mean by that is that's the spontaneous disintegration of an unstable nucleus. So, and it's what happens is it spits a particle out of the nucleus, okay, and it's accompanied by the release of radiation. So when a nucleus is unstable, it spontaneously disintegrates, and when that happens, something gets released from the nucleus, okay, and that whole process or that whole type of reaction is called a radioactive decay. All right, so now that we got some of the terminology down, we can start applying it. Okay, so these are different types of nuclear reactions. So we're just going to kind of go through several of these, and they all have a common theme that I think you'll pick up on. And so this first one we're going to call alpha emission. And by the way, so some synonyms here. So in this this unit, anytime I use the word emission, I can substitute that with the word decay. So you could also say or decay. So if you want to put that on your handout, that might be a good idea. Okay, so you could just as easily say alpha decay, but it's alpha emission is the type of nuclear reaction that's occurring. All right, so this is just an example of that. So you have this radionuclide. It's an unstable isotope of radium-226. And so if it undergoes alpha decay, it spits out this thing called an alpha particle. Now, an alpha particle is basically a helium nucleus. It has 2 protons and has a mass number of 4, so that means 2 protons and 2 neutrons. So it spits out one of those, and then what's left over is radon-222. So notice that there is some balance going on here. If I add the 2 to the 86, I get 88. And if I add the 4 to the 222, I get 226. All right, so there is balance with the superscript, and there's balance with the subscript. The superscripts on the left have to equal the sum of the superscripts on the right, and the same thing with the subscripts. There has to be balance. And that's because of the law of conservation of matter. You can't create or destroy matter. It is conserved. Okay? So the number of nucleons must be conserved in any nuclear reaction. So it's pretty easy. Like I said, you just balance the superscripts on each side of this arrow, and you balance the subscripts. And then, from the subscript, you can also get what these chemical symbols are. There's some memorization involved. Like you need to know that this thing that's got a 4 and a 2 is something we call an alpha particle, but not much memorization is involved. Okay, so in alpha particle emission, the mass number decreases by 4 and the atomic number decreases by 2. So you can see that right here. So we went from 226 down to 222, so it decreased by 4. We went from an atomic number of 88 down to an atomic number of 86, so it decreased by 2. Okay, so that's one type of emission reaction or decay reaction. The next one we're going to call is beta emission. Okay, so what happens there is a beta particle gets spit out of the nucleus. So we start with an unstable isotope, a radionuclide, in this case uranium-239. So it's unstable. So how does it deal with that? Well, it spits out this thing called a beta particle, okay, and then it's going to become neptunium-239. So how did we know it was going to become neptunium-239? Well, once again, things are balanced. The superscripts are balanced. So the beta particle has 0 for a mass number, because remember, a beta particle, well, maybe we should define what a beta particle is first. Beta particles are basically an electron that's born from the nucleus. Okay, so the characteristic things are that the atomic mass number, A, remains unchanged, but the atomic number increases by 1. All right, so what has happened is that in order to accomplish this, you have a neutron, okay, because remember the total number of neutrons and protons stays the same, 239, 239, stays the same. So what's happened is that one of those neutrons has converted into a proton. And the way it did this is it emitted this thing called a beta particle. So a neutron becomes a proton by splitting up. This basically splits apart into a proton and this thing called a beta particle. And again, there's conservation here. If you add these two together, 1 and 0, you get 1. If you add these two things together, 1 plus minus 1, you get 0. Okay, so what you have here is you have a way for a neutron to convert into a proton by getting rid of a negatively charged particle that has effectively no mass. Okay, well, we've heard about those before. They're called electrons. Okay, so basically, a beta particle is an electron, but it's an electron that's born from the nucleus. It's not an electron that was, taken from the valence shell of another atom or something like that. This is an electron that gets born, and it's born from the nucleus. All right, so that's what's going on in beta emission. In beta emission, you have a neutron converting into a proton, and it spits out a beta particle, which is essentially the same thing as an electron. Okay, and so again, because one of these neutrons has become a proton, that's why you see the atomic number go up by 1. So it goes from 92 to 93. That means 92 protons, and the product has 93 protons, because one of these nucleons, one of these from the set of 239, has changed from a neutron into a proton. So you still have 239 because you still have that total of 239 neutrons plus protons. But one of those neutrons has now changed identity and become a proton. Okay, so that's beta emission. Okay, well, you can also have something called positron emission, and a positron is essentially a positive electron, if that makes any sense. And so this is the symbol for a positron right here. So we still use the beta as the symbol, but in this case, the charge is a +1. Okay, and it still has no mass. It's still a teeny tiny particle. We consider as having a negligible amount of mass. And so here's an example of a positron emission. So let's say that we have polonium-207. All right. So if it undergoes positron emission, it spits out a positron. And so remember what we have to do. We have to conserve the superscripts and the subscripts. Okay. So the other product must be an 83, because this is 84 and I have 1 from the positron. So I need something that has atomic number 83 as the other product. Okay. And so then you can get the chemical symbol from the periodic table. Atomic number element with atomic number 83 is bismuth, Bi. And again, the superscripts are conserved. So since this is a 0, I use the same superscript that I had on the left over here. So since it was 207 in the polonium, it's still going to be 207 with bismuth. Okay, so everything is still conserved. All right. So they have the mass of the electron, which remember is not much. They're what we would consider to be a negligible amount of mass, but they have a positive charge. And so you may have heard the term antimatter, okay, maybe, you know, some previous science class or some, you know, sci-fi movie or something like that. Well, this is antimatter. This is the antimatter analog of an electron. And so in this case, what happens is you have, instead of a neutron converting into a proton, you have just the opposite. You have a proton converting into a neutron by spitting out this positively charged particle. And if you think about it, you know, neutrons and protons are very similar. They have about the similar mass. But what's distinct about a proton is it has that positive charge. So it becomes a neutron by spitting out its positive charge, by getting rid of its positive charge. So let me do a little example here, some examples on how to answer some questions about these nuclear reactions. So in this case, like I said, the key thing is to remember to balance subscripts and superscripts. So, and we also want to identify what type of nuclear reaction is going on. Okay, so if you look what's on the left versus what's on the right, so I'll do superscripts first. So I've got 12 over here on the right, and I've got 13 over here on the left. So I'm going to need something with a subscript of 1, positive 1, right? Because the stuff on the left has to equal the stuff on the right. So it's going to be a plus 1, okay? And 25 on the superscript, 25 on the superscript, so that means I need a 0 for the superscript. And then you just, like I said, you kind of memorize what these particles are. So that's a positron, okay? So a positron is what has a plus 1 charge, but no mass at all. So it's kind of like a proton and that has a positive charge, but it's like an electron and that has a negligible amount of mass. Okay, so this is positron. Positron emission. Okay. All right. So what about this one? So we know that it's alpha decay. Okay. So that's one thing I can go in and write down because that I noticed that it's spitting out the alpha particle. Okay. So I got to pick out what the other product is. Well, once again, if in alpha decay, the atomic number goes down by 2. So this 84 becomes 82. Okay. Because 2 plus 82 is 84. And so now I just need something to add to 4 to get 210. Well, that would be 206. Okay, 206. Okay, 206 plus 4 is 210. So I look up on the periodic table what element number 82 is, and that's lead. Okay, so you can use the periodic table to help you out. And so once again, 4 plus 206 is 210. 2 plus 82 is 84, and that's alpha decay. All right, but we can also use the products to predict what the starting material was. What is the reactant? So once again, my subscripts are balanced. So -1 and 7. So that's a 6. So I know it's going to have a subscript of 6. And 0 and 14. Okay, so that's 14 for a superscript. Once again, I just go to my periodic table and I look up what is element with atomic number 6. That's carbon. Okay, so this is the beta emission. Okay, so this is beta emission. Oops, it doesn't look like an E. Beta emission of carbon-14. Okay, so now let me erase all that and I will just go through it one more time. Okay, so the positron emission, the alpha decay, and the beta emission. Okay? All right, so it takes a little practice, but it's really not a very difficult thing to do, and this is kind of a big skill that you want to develop from this lesson. Okay, so regardless of where you're at, hopefully you got some of it done. I'll show you what the answers are. So, when uranium-238 undergoes alpha decay, this is the product, the thorium-234. When iodine-131 undergoes some sort of decay to become xenon-131, it went from 53 to 54, so it spits out a beta particle, beta emission. And then it's fluorine-18 that undergoes positron emission to become oxygen-18.
The electromagnetic spectrum is composed of different regions. And for example, the visible light that our eyes are sensitive to is this right here, but there's lots of other regions of the electromagnetic spectrum that's fundamentally the same substance. These are waves They have a dual nature, they're particle and wave-like, but everything from, the signal that you get from your cell phone and the microwave that you use to heat things up, and infrared radiation is essentially heat, radiated heat. UV radiation, you're familiar with that from like a sunburn. And then X-rays, diagnostic X-rays, people are familiar with that. But this is what we're going to focus on today in this lesson, are these gamma rays. Okay, that symbol right there is the Greek letter for gamma. And so gamma rays are the type of electromagnetic radiation that's given off with pretty much all of the nuclear reactions that we're looking at. Okay, so let's go ahead and talk a little bit more about gamma rays. Yeah, so like I said, we're going to focus on the gamma rays today. Okay, so gamma radiation, a couple characteristics that we want to remember and hone in on with this topic is that these are high energy photons, okay? And that energy that's in the photon, when it's absorbed in matter, what it does is it creates a lot of ions, okay? And those ions will go on to react with other atoms and molecules that create further ions. And so it's like a cascade effect. When the photon interacts with one atom, it creates an ion that has a lot of energy. And that ion will use its energy to create many, 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 many more ions around it. So the surrounding material tends to get damaged also, okay? So high energy photons that generate high energy ions and charged particles when they interact with matter. All right, so that's sort of the mechanism of damage from gamma radiation. It creates an energy, it creates an ion that has a lot of energy, and then that high energy ion goes on to damage other atoms and molecules around it by transferring its energy to those surrounding atoms and molecules, ionizing them, and so forth, okay? All right, and as I said already, that the gamma rays are generated by most nuclear reaction types. Now, the other usefulness is in imaging. And so this is where we also use these radionuclides, because remember that all those nuclear reactions spit out these gamma rays. And remember also that the gamma rays have a large penetrating range. They're not blocked easily by anything that it might encounter. And so the idea is that it can make it through the body. These gamma rays can pass through the body, and therefore they can reach a detector in some sort of medical instrument, some sort of imaging device. And so these are the radionuclides that are typically used, because we'll try and get it to a certain tissue in the body where we suspect there might be a cancer cell, and then it can spit out that gamma ray, and that gamma ray can be detected by these special instruments that we use in hospitals. Okay, and so again, you can see the different imaging that's done with these different radionuclides. And it's all based on the gamma rays that are spit out from the nuclear reaction. Okay, so one of those that's popular is it exploits the production of, it exploits the positron. And so just a little bit of a review what we mean by a positron. Again, we talked about this in lesson 2. The positron is like a positive electron. It is the antimatter analog of an electron. And so what happens, because it's an electron's antimatter cousin, when it finds an electron, which of course in the real world, electrons are all over the place, right? Whenever it finds one, it's totally annihilated. Both the positron and the electron are totally annihilated. And in the wake of that, it produces 2 gamma rays. So a positron and an electron find each other and they totally annihilate, and they create 2 gamma rays. And the nice thing about it is they go off, and this is physics, we don't get into this, it's beyond the scope of this course, but they go off at 180 degrees. And so that, because of that, it's very nice for pinpointing a location, right? Because of the 2 gamma rays are going off in equal energies, but in totally opposite directions. It's easy to pinpoint the location that the reaction occurred. And so it's very useful for imaging. So the energy of the nuclear reactions is released as gamma rays, and that's used in imaging, and that type of imaging is called positron emission tomography, or PET. Okay, so this is a widely used imaging technique in hospitals. If we were in the classroom, we would watch this video, but we won't do that. I'll let you do it. It's also hyperlinked in the handout, so I'll let you watch it. It's basically just like a very short video, maybe 2-3 minutes on how positron emission tomography works, and just would encourage you to take a look at that. Okay.